Okay, what we're going to work on in this problem is finding a normal line and a tangent line to this curve x squared cosine squared y minus sine y and equals 0. And the cosine squared y is just another way to show an exponent, okay? We don't generally write that cosine squared y with the squared part at the end, because then we're confused, like is the squared on the y or is it on the cosine or what's going on? So normally mathematicians are going to write that as cosine squared y. Like it looks right here, okay? Notice with x squared and cosine squared, you have product rule going on. So we have to determine what u and v are. I'm going to pick u to be x squared, u prime to be 2x. I'm going to pick v to be cosine squared y. And v prime then is going to be what? 2 times the derivative of the cosine, which is negative sine, okay? And times the derivative of the y part, which is dy dx. So how does all that work? Well, I'll show it you again with the u substitution. I'm going to let u equal cosine y, so du dx is negative sine y. And then when I come back over here and substitute all of that in, this is what it looks like, okay? So v prime is this really long derivative right here. Negative 2 cosine y, that's my base part, that's my big function part, times the derivative of the cosine now, which is sine, times the derivative of the y, which is dy dx. It's a big deal, okay? But that gives me u and v, so I can do u times v prime plus u prime times v, and that's that first part all in blue, okay? That's the first product rule derivative is all in blue. And then the derivative of sine y is cosine y dy dx, okay? Now I want to get dy dx together by itself on one side of the equation. So what I'm going to do is subtract everything over that doesn't have dy dx in it, and that's why the cosine squared 2x cosine squared y moves. Everything else has dy dx in it. Once I get that negative 2x cosine squared y on the other side, I've got dy dx all by itself on the left. I can factor it out, and when I do that, I can divide both sides by what dy dx is multiplying with, which is really, really, really huge, okay? And that's okay. It could be big, long, and nasty, but that's what my derivative looks like, okay? The other thing that I can do now with that big, long, nasty derivative is factor out a cosine. I've got a cosine y in every single part, so I can factor all that out, and now my problem is a little bit simpler to look at and not so gross, okay? Now the whole thing here is that I need a tangent and a normal. Well, what we found by going through this whole derivative process, and you'll see me as I work it backwards to the left here, we found the equation to find slope of a tangent line. We just need the specific point the tangent line is at. Well, hey, they gave it to us. It's 0 pi. 0 goes in for x, pi goes in for y, and when I plug those things in, I find the slope of the tangent line, which in this case is 0. What does that mean? That means that I have a horizontal line, and in a horizontal line, everything it has the equation of the y coordinate. So for this particular instance, the tangent line is y equals pi. The normal line is 90-degree perpendicular to the tangent line. Well, that's going to take on an equation where we have all the x coordinates, which in this case is 0. Okay, so that's how you find a normal line and a tangent line to a curve.